Hello everyone, my name is Haotian. I'm a graduate student from UC Berkeley, and today I'm very glad to present our paper Q-learning algorithm for mean field controls with convergence and sample complexity analysis in this workshop. So this is also a joint work with Professor Xinguo from UC Berkeley and Xiaoli Wei from UC Berkeley and also Renyuan from Oxford. Today, this will be the outline of our talk. In the first section, we will discuss the connection between the multi-agent reinforcement learning with the mean field control problem. And in the second section, we will go to the algorithm design part and show the convergence and sample complexity results. And lastly, we will show numerical experiment showing the performance of our algorithm. So I hope everyone is convinced with the fact that nowadays we are actually interacting with multi-agent systems intensively. For example, in the autonomous car setting, we want to let these cars collaborate with each other so that they can make the traffic flow fast and safe. And also in this network congestion problem, the senders are trying to sending message to the receivers through a shared link. And they don't want to make this link too crowded because this will result in some loss in the information. But also at the same time, they want to make the sharing as fast as possible. So in all these scenarios, we notice that there are a large number of agents interacting with each other, and they are collaborating with each other to fulfill some common goal. And this gives us the motivation to define the collaborative MARL. In this setting, we have a group of agents, and at each round, they take actions. And based on the population, state, and action profile X and U, they will receive rewards and transit to the next state based on the population's policy and state. And the policy we are seeking in this setting is some map from the population profile, state profile to a randomized action. Here it is collaborative in the sense that there is a central controller who is trying to maximize the population reward defined here. This problem is well known by its difficulties, which is called curse of dimensionality. This means that if we just apply the classical Q-learning algorithms to this problem, the resulting sample complexity will increase exponentially with respect to the number of players in the game. So in order to resolve this problem, one potential consideration is to do the mean field approximation. In the mean field setting, we are assuming that all agents are identical and interchangeable, and they depend with each other only through the empirical distribution of state and actions. If we take this n to be infinity, this will become a mean field control problem. In this problem, the central controller observes the population distribution mu, and each single agent will take action based on the central controller's policy. Now the policy depends not only on the agent's state, but also on the population distribution. Also now the reward and the probability transition matrix also depends on the single agent's state and action as well as the population state action distribution. The mean field control problem from the single agent's perspective is more carefully defined here, but more importantly, we observe in our early work that if we lift the finite state action space to their perspective distribution space, Px and H, this will result in some a control problem from the central controller's point of view. And also at the same time, we need to aggregate the reward over the whole population as well as aggregating the dynamics. And the dynamic programming principle in this case is studied early in our previous work. It's saying that if we define a Q function for the central controller in this usual setting, the resulting Bellman equation is in this form. And here notice that the Q function for central controller is now depending on the state distribution mu as well as this H. which can be viewed as the action for central controller. And based on this DPP, we observe this MFC is different from classical MDP in 3 perspectives. First, now we are dealing with continuous state space. In order to approximate the unseen data, we use kernel regression, which is a very common techniques in the statistics and the machine learning literature. And also, in order to deal with the continuous action space, we want to avoid optimizing over the continuous space in our Bellman iteration. So we will just optimize on a finite epsilon net on the action space. And also, now we have deterministic dynamics. The determinicity comes from the aggregation over the population. So we will also actually take advantage of this property to reduce our sample complexity. Now, based on this observation, we define this approximated Bellman operator, which is different from the traditional Bellman operator from 2 perspectives. One is that now we are optimizing over a finite epsilon net on the action space. And also, we use the kernel operator to approximate unseen data. So basically, the algorithm consists of 2 stages. In the first stage, we get sample data from for some epsilon net in an online fashion. And in the second step, we use the Bellman updates to find a fixed point for this BK. And the convergence and complexity results saying that under mild assumptions for each epsilon prime greedy exploration policy, and with probability at least 1 minus delta, and for any initial state distribution mu and epsilon net, after this many time steps, the algorithm will converge to some good approximators to the true Q function. And the arrow is bounded by some constant times the epsilon. And the constant is some, and C is some constant independent of this model parameter. And also the sample complexity depends only polynomially on this model parameter. A quick remark here is that there are three sources of approximation errors in the algorithm. One is kernel regression, one is discretized action space, and the last is the estimated data. Basically, we will, in the analysis, we take care of these 3 parts individually and put them together to get these results. Compared with different complexity results for different types of algorithm, we have this table. So you can see the first 2 works all use the mean field approximation, but our sample complexity is much better than the second one, because in the second one, they didn't take advantage of the deterministic dynamics, and which results in a worse sample complexity. And also the third line is something we have mentioned before, which means we just use the classic Q-learning algorithms on the unpaired games, which will result in a terrible sample complexity, increasing exponentially with respect to the number of players. And in the last line, their work actually tackle the curse of dimensionality problem from a different perspective. They utilize some local structure of the players. They are actually assuming that the players can only interacting with each other very locally, so that they can have a better sample complexity guarantee compared to the vanilla version of Q-learning. But here, this quantity f can actually still scale as large as n when the agents are not interacting locally. So in some sense, this arrow, this sample complexity results are model dependent, but our work is model independent, model free. And in a numerical experiment, we come back to the network congestion problem we defined at the very beginning of the talk. And we apply the mean field control policy we learned back to the n-agent version of network congestion problem. You can see the performance of our algorithms is much better than other previously proposed algorithm for this problem. And especially when the number of players is large. And also in the second graph, the black dashed line is the true capacity of the of the shared link. So the closer you are to the true capacity, the more accurate you learn. So you can see here our blue result is the closest one. I think this is what I want to share with you in this talk. For more details, please feel free to find these two references online. And also, if you have any comments and remarks, I'm looking forward to talking to you in my poster session. Yeah, thank you very much.